Hello and welcome back to sections 19.1 through 19.2. In this video we're going to be demonstrating how to use the principle of impulse and momentum with example 1 here. So example 1 has this wheel and it's going to be rolling. We expect this to roll to the right, so we expect that, so it's going to be 6 seconds later. So 6 seconds later we expect this to be, well, if that's a straight line, it'd be over there to the right. That's a little better. So we'll be over here somewhere. So we expect it to kind of move to the right in a rectilinear form. We're going to have some forces on here, so it's not going to the ground, so there's going to be a reaction force, which is going to be a normal. We have this moment here, so this torque that's being applied to the wheel. The wheel has some weight that we're given in the problem, and then there's also a friction force that is keeping the wheel from slipping. The wheel does not slip. And so we're only asked for angular velocity and the friction force. So because we're not asked for acceleration, this is a really good problem to use the principle of impulse and momentum. So let's jump over to the visualizer. Alright, so I've redrawn it here. So we have our free body diagram. I've noted our unknowns here. So the friction force, the normal force, and omega. There's also alpha, but we don't need to find alpha. They call the center O, but I went ahead and relabeled it as G. And I called this bottom point O because it's an instantaneous center. So I wanted to note that it is a point of zero velocity. I have my moment of 300 Newton meters here. Alright. So what we can do, the first thing we want to find is this friction force, F naught. We were not given mu s, so we can't use the relationship for F max or anything like that. So instead, what we should probably do is we should probably do a principle of impulse and momentum in the x direction to get started. I only have this force in the x, so we're going to have mass velocity g in the x at state 1. So this is the generic equation that we covered last time, integral all the f of x's in d2, so all the x components of our forces, equal to mass velocity g x2. And so what this should do is this should get us F naught. It's the only force in the x direction. So we know that this thing starts from rest, which means that this will have some initial velocity of 0. This term, we get only the x components. I've already established that this is in the y, this is in the y. There's no other forces. This is not a force, so it's just the F naught. So we're going to integrate F naught dt. Our time is 0 to 6 seconds. All of F naught exists in there, and it will be positive because it is to the right, and we assume that the thing is going to the right. So I will get a positive friction force. And then our ending will be, our mass is 300 kilograms, and then we have this velocity g, x2, and unfortunately I do not know that yet, but I can relate it back to the omega that I'm going to also have to find. So if I kind of draw our diagram, again we know this is a fixed point. I'm going to have some velocity at the center of gravity. I'm going to have some omega. This is all the same way that we've assumed and diagrammed stuff. And I have some r here. Then I know that that Vg is equal to omega r. So I'm just going to rewrite it like that so that I have this already in terms of the stuff I'm going to find in a second. So we're going to get omega 2 and r, and we know that r is, I didn't put it on here, but r is 0.6 meters. So we can sub in a 0.6 for this. And we can simplify real quick, but it won't really do much until we find omega 2. So I guessed wrong is where we start. So we'll have to come back and solve this once I find omega 2. We can find omega 2 using an angular impulse and momentum equation. We could go in the y direction, but that's not going to find anything we want to find. It's only going to show us that the gravity is equal to the normal. Like that's about all. We're going to find the weight equal to the normal, sorry. That's all we're going to find in the y direction, because there's no velocities in the y direction. So that's not a useful equation. So the next one we're going to do is we're going to do one of our angular impulse and momentum equations. This is the one we actually just started with. So we need to be a little bit strategic about this. If I do this about g, then I will have this moment, and I will also have the moment produced by f naught. I don't know f naught, so I'd rather not put f naught in there as well as omega. I'd have two unknowns. If I do it about point O, then the only thing that produces a moment, because n and f both apply here, and the weight goes through it, so none of those will produce a moment. So only this 300 moments that I know. So I will find omega if I do it about the point O, the instantaneous center. So that's what we're going to do here. So sum of the h naught at 1 plus sum of the integral of the moments about O, integrate that over time, sum of h naught 2. So this is all for our instantaneous center. Let's expand these out. I only have one body, so the summations don't matter. So we just get I naught omega 1 plus, we only have one moment, which is why we did it this way. So we just have that 300, so we're going to integrate that 300 dt. So that 300 is acting opposite of the way that I just said. So we could either call this negative, or I could just fix this. And I'm just going to change this because I've defined everything. I've already defined omega this way, so I'm going to have to define my omegas as well negative if I leave it like that. So I'm actually going to change this so that I don't have to put a bunch of negative signs in. So omega has been defined clockwise. This moment is clockwise. Let's just assume everything is clockwise. And if it's not, then we'll add a negative sign. All right, so now this is going in the same direction as this arrow, and I don't have to do any negative signs. It goes from 0 to 6 seconds. And we get I naught omega 2, which is what we want to find. So again, this starts at rest, so omega naught is 0. Sorry, omega 1 is 0. And on this side, so just kind of solving this, I will get 300 t from 6 to 0 equal to I naught. I naught will expand, so I need to use parallel axis theorem because I was given there we go. I was given the raised gyration about the center of gravity. So note that in the problem they call it k naught, but originally they also called the center 0 or not, O whatever. So this is about O. I've relabeled this as O. Don't get confused. So O is our point down here, G is our point up here. The raised gyration they gave us was about the center of gravity. All right, so we can rewrite I naught as Ig plus mass distance squared, and then omega 2, which is what I want to find. All right, so that becomes 300 times 6, which I believe is 1800. And our I about the center of gravity will become our kg squared mass. So I'm going to have mass for both of these. And then plus mass, and then this will become radius, because that's the distance that we move. It doesn't matter if it's positive or negative because we square it. We have omega 2. So we plug in some numbers, and we will be in good shape. So our k, so they gave us 400 millimeters, but we want to use 0.4 so that we're in meters. So for 0.4 squared, we have 300 kilograms. Again, 300 kilograms. We could probably move that out, actually. Our radius is 0.6 meters. And omega 2. So when I solve this for omega 2, I will get 11.54 radians per second, and it's positive, which means it is in this direction. So that's the first thing I wanted to find. And now that I know that, I can come back up here, I plug in my 11.54, and I solve this for f naught. Because again, it's just 6 f naught equal to a number. So f naught will become 346.2 newtons. Let me just separate that. All right. So that is how you apply the impulse momentum in the linear direction and in the angular direction. And again, just a friendly note: if we would have done, we should have done the impulse momentum about 0.0 first, done the second. If you do this about g, you will get f naught producing a moment as well as this couple moment, so you'll have two terms show up in your integral if you do that about g. All right, if you have any questions, feel free to reach out.